Welcome back. We're going to go ahead and take a look now. This is going to be part 3 of line integrals, so we're going to go ahead and look at line integrals in a vector field. And so, first question is, what is a vector field? A vector field is some space, whatever dimension it may be. It could be in 3, 4, 2, or 1 dimension. But that space not only has a magnitude assigned for every ordered grouping of coordinates, but it also has a direction. So with the scalar field, we remember that if we had an ordered pair in 2 dimensions, that we would have some magnitude that would output, but that magnitude had no direction. Whereas with a vector field, each magnitude for every point has also a direction. And so the idea of integrating a line in some sort of vector field is much different than in a scalar field because we have a sense of direction now. So here's my curve C. The curve C is going to be also thought of as the parameterized curve, the parameterized vector curve R of t. And so let's take a look at R of t down here by itself. So I know I mentioned this in another video, but I can't stress it enough. The vector R, this vector here, as you plug in units of time, does not point in the direction of the curve. It actually points from the origin to the spot on the curve that it's at currently. Which is why we had to do all that work to find the unit tangent vector, because the vector R itself just points at where it's at, where the line is at now. It doesn't point along the line of travel. However, if we look at some R1 and R2 of different values of time, we'll notice that the segment dr is in the direction. So in other words, the change in R as we go from R1 to R2 is tangent to the curve. And so what we're interested with in a line integral is figuring out, as we travel along this line, how much of the force of the vector field is going to be in our direction or against our direction. And so for that reason, you do need to indicate what the direction of travel is. And as you can see, if we zoom in on, let's zoom in on a little point in here somewhere where the vector field is pointing. So the vector associated with that point is pointing to the right. We are trying to travel almost straight up. And so this will be our dr, and this will be the force at that value F. And what we're looking for is how much of that force goes in our direction or against our direction. And if you'll notice, if we do a projection of F onto our segment dr, projection is just the 90-degree right triangle, you'll notice that there is, in fact, a little bit of force going in our direction, which is better than nothing, right? So to find out what the magnitude of the force is in that direction, or the vector in that, it could be any vector. But anyways, we're going to take the dot product of F and dr. So in other words, we're going to figure out how much of F is in the direction of dr, and then we're going to multiply that amount by dr. And so that's the vector line integral. It's F dot dr. And once again, this is kind of the simplest form we can write it in, but it's not very useful to us because we have our vector curve equation in terms of time. It's parameterized in terms of time. And so I don't see any time values in here. So the key here is another trick. If you'll remember, the change in the curve, the change in R with respect to time, is equal to velocity. Now we can rearrange this in a way that I'll admit is not very mathematically correct, to find that dr equals v dt. Now this is true. The way I did it isn't necessarily sound mathematics, but this is a true statement. So the dr is equal to v dt, and so we can do a substitution for dr. We can sub in v dt. because velocity is a vector, it will take over the place of dr in the dot product. So now we have f dot v all integrated with respect to t. And now a and b are no longer boundaries in terms of position, they're boundaries in terms of time on our function r of t, which makes this whole process a lot easier. So that is the vector line integral. It's useful for calculating things such as work, very important in Maxwell's equations and integration. In integral form, these pop up all the time, so important thing to know. Hope you have a good day and this was helpful.